Hello and welcome back to some more physics. So Tane has a toy car track set, amazing, I do too, it's right next to me. But he has a banked curve, that is awesome, and a vertical loop, the classic level 3 physics concepts. We can assume sideways friction on the tires is negligible, so the only force keeping it sort of acting inwards would be the support force, and we're told the toy car has a mass of 0.120 kilograms. Part A. On the diagram, draw a vector to identify the net force that is responsible for the car going in a horizontal circle. Right, so it's banked, it's going to come sort of towards us and sort of move around to the right, go around back around the bank, like that. So it's top down, we see a circular motion, and we know for circular motion there needs to be a centripetal force, which is a net force acting inwards to the center of the circle. So that's what it would look like top down. Now side on, it's a little bit different. It would be going this way. Let's get a straight line there. There we go. So that is our F net. Is that all it's asking? I think so. Yeah. I mean, while we're here, we could draw like a weight force and a support force, and now this net force, let's just adjust that to be accurate. That's our net force, that's our weight force, that is our support force. But the only one we had to draw for this was F net. Cool. Alright, that is an achieved question. Easy. Now we're told that the banked curve has a radius of 0.75 meters. Okay, so the radius of the circular track. And we're asked to calculate the banking angle, ignoring friction, right, which is why I didn't draw that on our vector diagram. Well, it's moving at a speed of 1.55 meters per second. Cool. So I'll show you two ways of doing this. The easy way is if you just know the formula. The harder way is if you forget the formula and you just need to derive it yourself. Cool. So the formula for the speed relating to the radius, gravity, and bank angle is v squared equals the radius times gravity times tan theta. Or you may have seen it as v equals r times g tan theta square root. Alright, they're the same thing. If we square root both sides, we get this one. Cool. So this equation relates the speed, radius, gravity, and bank angle. Ooh. That up a little bit, and we are trying to solve for the bank angle, so tan theta. So let's divide by radius times gravity, v squared over radius times gravity, and then the angle would be the tan inverse of v squared over radius times gravity. Putting in what we know, speed of 1.55 squared divided by the radius 0.750 times, assuming it's on Earth, 9.81, would give us a bank angle of, if we're in degrees, 18.1. If you're in radians, you can just write the value and then rad. Great, that is the easy way of doing it, if you know this equation. Now let's just derive that equation because it's pretty straightforward now that we have a vector diagram. Let's have a look at that again. I'll just draw it to the side so we don't need the car anymore. Let's try and draw it to scale. Oh, that's a miss. There we go. All right. So we have the weight force acting down, mg. Yeah. We have the net force acting inwards, mv squared over r, the centripetal force. And if I just draw this component up like that, and if we move our centripetal force, oh, that's too much. Move our centripetal force up to here, we can just see that it's like a component of the support force. Great, so we have mg, we have mv squared over r. Yeah, two sides of our right angle triangle. And this angle right here is actually the bank angle. So the bank angle would be the tan inverse of opposite, so mv squared over r divided by adjacent, mg. So tan of the angle is the centripetal force, so opposite over the weight force, Fg, which centripetal force is mv squared over radius, weight force is m times g. You'll notice the masses cancel because this is like mg over 1, and when we multiply by the inverse, one's mass is in the numerator, one's in the denominator, and we're left with v squared over r times g. And would you look at that, we are back to here. Yeah. So for this question, you are welcome to just state the the bank speed and angle equation if you know it. If you don't, you just derive it from this right angled triangle where the opposite is centripetal force, the adjacent is the weight force, tan of the angle equals opposite over adjacent. And that is a merit question, right? The excellence version of this question would ask you to derive the equation. So you do need to know where it comes from. Awesome. Let's move on. Oh, onto the good bit. Now we have the vertical circular loop, right? It's a bit more challenging than horizontal circular motion because the support force is changing throughout the loop. Yep. So that's an added layer of complexity. Part C. Explain why the person sitting in a car on the actual roller coaster would feel heavier at the bottom compared to the top. And it gives us a nice hint. Draw labeled vectors at the bottom and at the top. Great. So, let's do that. What do you have? Well, you have mass, so you will have a weight force. Let's put that in green. Okay, that hurts my eyes on the red, never mind. Let's put that in blue. You got a weight force, and your weight force does not change unless you throw up, but please don't do that. Okay, gross. Your weight force is constant throughout the motion. Now, what is your reaction force? Before we can answer that, let's think about what the net force is. Right, the net force is a centripetal force because you are, in circular motion. Thank you. And so your net force is always inwards. See? And if you're traveling at the same speed along the loop, that wouldn't change. In reality, this does change, but we are simplifying it by saying the centripetal force is constant, it's uniform, always acting inwards. So at the bottom, the net force is up, and at the top, the net force is down. Okay, and so to get the net force, we need to add up the individual forces. And so looking at the bottom, currently weight is down, so to go to FC, we need to go up by the weight force, and then up by Fc. And this is our reaction force, Fr. Now at the top of the loop, in order to add to Fc, we only need that much of a reaction force, Fc. So notice at the bottom of the loop, the support from the track is pushing you up a lot to overcome your weight, as well as add enough for the centripetal force, whereas at the top, your weight is doing most of the or taking up most of the net force, so the reaction force is much less. Okay, and when we say how you experience weight, when you feel heavier, it's not your actual mass times gravity, it's your reaction force. Yeah, if you've ever been in an elevator and it goes down, and then when it decelerates, right, the reaction force going up is greater and you feel heavier, you feel like you're sinking into the ground a bit. Exactly the same on a vertical loop. So let's put that into words or bullet points. So the feeling of weight depends on the support force or reaction force or the normal force. It's got many names. At the bottom, let's use S for support force. The support force is greater than the weight force for Fc, for the centripetal force to act inwards. And again, back to our diagram, the black arrow, Fr, is greater than Fg, because when you add them, the result needs to be upwards in order for this circular motion to occur. So they feel heavier. All right, let's do the same logic but for the top. So at the top, this time the support force is less than the weight force for Fc to act inwards again. And if you want that as an equation, Fc would be Fg plus Fr, whereas at the bottom, Fc is F reaction, take away the weight force. And so at the top, they feel lighter. And so if reaction force was 0, they would feel weightless, because the only force acting on them is their weight, right? So they'd be momentarily in free fall. All right, and this was an excellence question. So let's just summarize this one. Going back up to the diagram. As you approach the vertical loop, your weight force is your weight force. It's always constant at the bottom and the top. In order to follow the circular motion, the circular path, we always need a net force acting inwards. So at the bottom of the loop, it's acting upwards. At the top of the loop, it's acting downwards. To ensure that, what changes is the reaction force. So at the bottom, reaction force is very large, whereas at the top, it can be very small, depending on your speed. And so you feel heavy at the bottom due to the reaction force being large. You feel light at the top due to the reaction force being small. And so we discussed that. We started by saying The feeling of weight depends on support force, and then we described it for the bottom and the top. Alright, let's move on to the last question, which is another excellence question. Very generous. The toy car has a mass. Great. Who would have thought? And the vertical loop has a radius. 0.25. Calculate the speed with which it must approach the loop to be able to go around the vertical circular loop, such that the car seems weightless. Okay, that is a key point. Back to our diagram. As I've drawn it, this car is not weightless because it has a reaction force. It would be weightless if... Come on. Hello? Go away. Oh my gosh, let me just add to it. If the weight force was equal to the net force. That is the definition of weightless. Okay, and that does simplify our calculation. So, at the top, we know that the weight force must equal the centripetal force. That's this bottom part here. And so let's just put in the equation. So for weight force, mass times gravity. For centripetal force, mv squared divided by the radius, divide by mass. And we can solve for speed. So multiply across by r. So v squared equals r times g. Alright. And we can square root as well. So if the velocity is equal to the square root of the radius times gravity, at the top, the weight force, Fg, would be equal to the centripetal force. Right? There would be no reaction force. And do we have R? Yep. And we know G, so we can solve for that. So V at the top, so I'd use VT for V top. No, I won't. I'll use V top, because that's even clearer, and it's only 3 letters. Equals radius, 0.250, 50 times gravity, square root. Where's my trusty calculator? Shift square root, brackets, 0.25 times 9.81, close bracket, 1.56605. Cool, so I'm not rounding it fully yet. I'll do that at the end. Meters per second. Great, so we know how fast it needs to be traveling at the top. Now, let's have a think. What energy does it start with when it's at the ground level with some velocity? Well, it starts with kinetic energy, EK initial. And what does that go into? Well, it's gained height, right? So it has gained potential energy. However, at the top, it still needs to have some velocity. So it also has K top. And I'll do K bottom. K bot. Yeah. So its initial kinetic energy at the bottom transfers into both potential energy at the top as well as kinetic energy at the top in order for it to have this required speed. And so with that, we can work out the speed at the bottom. So I'm going to do this in one big equation. However, you are welcome to split it up. But I feel one large equation nicely sort of summarizes this line that we've just written together. Wow, let's be honest, I wrote it. Alright, let's move that up here. So EK bottom is half times the mass times the bottom speed squared must be equal to the potential energy, mgh, plus the kinetic energy, half mv top squared. Okay, I notice there's a mass in every term, which is wonderful, so that cancels. I could times everything by 2, so v bot squared. So timesing by 2 gets rid of this half, but now we have 2gh. 2 times half is 1, so gets rid of that, v top squared. And we are solving for the speed at which it must approach the bottom. So we are solving for v bottom, v bot. So last step is just to square root. So v bot equals 2gh plus v top squared, all square rooted. And now we can put in the values. So 2 times gravity, 9.81. Height, what would the height be? We know the radius is 0.25. The height would be a full diameter, so it would be twice the radius. So 0.5. 2 times g times h plus the speed at the top, which was 1.566, etc., squared, and all of that is square rooted. So I have my previous answer, so let me just square that. So that's the v top squared, and I will add 2 times gravity times height, and then I will square root the answer to give 3.50 meters per second. And let's think, is that rounded appropriately? So everything that was 3 sig fig, 3 sig fig, yeah, so rounded to 3 SF. Looks good to me. And that is an excellence question. So let's step through it one more time, and I'll point out the achieved and merit points. So the question importantly says that it seems weightless at the top. So we need to state Fg equals Fc. Right? Weight force equals centripetal force. If that's the only thing you wrote, guess what? You just got an achieved point. Right? That's pretty generous. Further to that, right, we actually put in mg for weight force and mv squared over r for centripetal force, and we solved for v. And this v corresponds to the speed it needs to be traveling in order for it to be weightless. So we then calculated that to get 1.566 meters per second. Cool. Then, if you worked out its kinetic energy at the top, using half times mass times the speed squared, that would be a merit point. Yeah, but we didn't do that right away. We actually reasoned about the energy transformations. So it started with kinetic energy at the bottom, and that went into potential energy plus less kinetic energy. Right, then it started with. We put in the equations for kinetic energy, potential energy, being careful with our labeling, so V bottom and V top, and we solved for V bottom, which gave 3.50 meters per second. Awesome. Well, that is this question done. I'm going to go play with my Hot Wheels, and I'll see you guys later.